are CHs. Okay? CHs, and they tend to straddle 3,000. And what makes it so you get a CH on the bigger side of 3,000? Well, that's if it's an sp2. Remember I said the bond gets a little bit stronger the more s character you have. Okay, so if it's a carbon-hydrogen bond, and this carbon is sp2, then it's on this side of 3,000. Okay? If it's a carbon-hydrogen, and it's on this side of 3,000, right around 2,900, then it's a and it's an sp3 carbon. Okay. All right. One of the absorptions that is really useful out of IR, I mean there's lots of them, but is carbonyls. Carbonyls always give you a very strong peak, right? A carbonyl is a carbon-oxygen double bond. And there's a bunch of different functional groups that involve carbon-oxygen double bonds, right? There's esters, there's ketones, there's aldehydes. Have you guys done, yeah, you've done functional groups. Okay. Subtle variations with those types of functional groups, you know, the difference between a ketone, difference between an ester. For the time being, I'm not going to get into that. And I should have mentioned, Dr. Organ will do a much more thorough job of discussing infrared spectroscopy, but it's good analysis for aspirin, so we wanted to put it in here, and we wanted to give you at least just a sort of a quick and dirty passion of how this works, what to look for. All right, so 1670 to 1820. Okay, that's carbonyl. And then, I haven't been indicating it in terms of is it strong or is it medium or is it weak. If I draw it down near the bottom of the scale, then it's strong. Okay, carbonyls are strong. CHs tend to be strong. These tend to be fairly strong, but since they're spread out over a wider, they don't go down quite as far. Okay. The next one, it's a little bit weaker. I would say it's weak to medium, and that is carbon to carbon double bond. Okay. All right, and that is 1620 to 1680. These are rough sort of ranges that I'm giving you. So, you know, if you made a molecule, it's an alkene. And so you're looking for an alkene absorption and you get 1600, don't automatically discount it because, oh, you know, Gideon said it would be, you know, in that range, all right? You can see variations beyond these ranges. Okay. And, you know, why do you see variations? Well, there's other stuff attached to that. Yes, it's a carbon-to-carbon double bond that's vibrating, but there's other stuff attached to it that's throwing off that whole vibration, right? So there's going to be a uniqueness to it depending on what particular molecule you have. And there's 10 million known ones, right? All right, just a little bit farther down. I should move this. So that's more like 1500. Something like that. The scale of all of them, right? All right, so just a little bit to the right of alkenes, okay? I should say specifically this is alkenes, is the double bonds of aromatic compounds. Right? There's lots of different examples of aromatic compounds, but that's sort of the simplest one to convey. Yeah. So you have carbon-to-carbon double bonds in this, and so they have a slightly different range. 1400 to 1600. So aspirin, you remember the structure of aspirin, we would expect aspirin to have some peaks in this range, okay? It might not just be one, right? Because there are 3 different distinct types of carbon-to-carbon double bonds in aspirin, okay? In carbon-to-carbon aromatic double bonds. But in any case, we would expect to see some peaks from your aspirin in this range, right? We would also expect to see 2 peaks in this range, right? You have a carboxylic acid and you have an ester. Okay. All right, and then this range here tends to get really crowded. Okay. Out here, things are more spread out kind of nicely, all right? But you get a lot of absorptions in this range, okay? And sometimes you can get useful information out of it, okay? But sometimes this gets less and less useful, okay? Because there's so many peaks. They tend to be weaker than some of the other peaks at higher frequencies, okay? One thing that we do, and I'll give you a couple peaks in here, and you know, later in the year we make a compound that has a nitro group in it. In a nitro group, you get a very strong peak in this range. Okay, so it's not that the individual peaks in here are never useful. They just tend to, on the average, be a little bit less useful than the ones up here. But what this range is definitely very good for is acting like a fingerprint for your compound, okay? So, for lack of a fancier way of saying it, this range for your particular compound may be really funky, you know, and have lots of peaks, and it's kind of hard to make a lot of sense out of it. But the funkiness of this area for a particular compound should always be the same. So, while you may not be able to look at individual absorptions here, you ought to be able to look at it and say, yeah, the overall appearance of it looks like aspirin. Does that make sense? That's why we actually call this the fingerprint region. Okay. All right, but there are a couple useful peaks that are in this fingerprint region that I want to include, especially since they're important for it. And here, one there. All right, and this is carbon to oxygen single bonds. Okay, we got carbon to oxygen double bonds up here, carbon to oxygen single bond. Okay, and if it's a carbon to oxygen single bond for an acid, a carboxylic acid, okay, these were obviously chosen because your molecule has an acid. 1210 to 1320. And for an ester, it is about 1000 to 1300. Okay? Make sense? So one of the things for your assignment that you're going to have to do is you're going to take an IR spectrum, and then you're going to look for, I mean, what are the kinds of things you could have on your molecule? You've got carbonyls. Okay. You've got carbon to oxygen double bonds, or single bonds. Okay. You've got sp2 CHs. All right? You should have an OH. All right? And so you're going to want to look at your spectrum, and then what we tend to do is we tend to draw. Oh, okay. I'm looking for a carbon to oxygen double bond. Oh man, here it is. And so on your actual spectrum, what you're going to do is just draw C double bond O. You know, you're going to try to identify that peak. What students sometimes do, I don't know, I can't remember if they do it in the aspirin one as much as they go, you know, perhaps Dr. Organ's given them a chart that they've looked up on the internet and they found a chart and they found, aha, I have a selenium nitrogen double bond comes at about 1,000. And I see something at 1,000, selenium nitrogen single bond. Where did the selenium and nitrogen, you know, it has nothing to do with, they just looked at a chart, found that, oh, okay, there it is. You know what I mean? Your starting material doesn't have selenium in your product. So you want to be thinking in terms of, now you very well may have unreacted starting material, okay? And the next analysis that we're going to talk about will be better at giving you that impression. So that's possible. But when you're looking at an IR spectrum, you want to think about, you know, what are reasonable bonds that I might be looking for. Okay, does that make sense? All right. Okay, so that's it for IR. And like I said, I'm going to show you the video if you haven't had a chance to look at it on how to operate it. I'll do that after you guys get going. So the next thing we're going to talk about is thin layer chromatography. Again, in Gen Chem, you did a really crude chromatography. It doesn't work terribly well. It's not one of my favorite of the Gen Chem experiments. Right? You used food dyes. Do you remember that? And you sent it on paper, and it made this thing, and you were supposed to hand it as an assignment. You know, like, I don't know, it looks like a rainbow smudge. You know? This past summer, I had to do all the experiments on video and everything like that. And mine didn't look any better. And I've been doing thin layer chromatography for years. So, okay. So, we abbreviate thin layer chromatography just as TLC. Okay. And anytime you use the word chromatography, that means to separate things out. Okay. In chemistry, whether we're doing synthesis, which is what you guys did last week, or you're doing natural products isolation, you're going out into the world and looking for the next cure for cancer. Okay. A fundamental problem we face all the time is separating mixtures. We've got more than one thing in there, and we want to separate them out. We may want to separate them out just for analysis, just to see, okay, how many things are in there. But we may also want to separate them out, like we want to isolate, you know, a particular compound. Okay? So anytime you hear the word chromatography, you're separating. It invokes the idea of separating mixtures. All right. And so what we're going to do is, rather than just use you know, cellulose paper, we're actually going to use these TLC papers that have silica gel glued onto the face of them. Okay. So silica gel is very polar and sticky. Especially to polar compounds. The structure of silica gel is kind of a polymer lattice of silicon to oxygen bond. Well, maybe not. Okay, and so has Dr. Horman talked about intermolecular interactions yet? You do talk about it in Gen Chem. That's where you have, you know, you have two molecules, and one part has a kind of a partial positive area, and this guy has a partial negative area, and so they stick to each other because opposite charges attract. Okay. That's the general idea of intermolecular interaction. All right, so oxygen silicon is definitely a polar bond, so there is a partial negative charge on all oxygen. If you remember back from Gen Chem, oxygens and OHs can actually do a special. Oh shit, sorry.
I was like, he's being really quiet.
Yeah. Are you okay? I'm teaching. What did you say? I'll be done teaching in about 15 minutes, okay? Do you need to go to the bathroom? That's all I'm worried about. Whatever else is, he can wait. But that's the problem. Then I have a problem. Okay. You may remember that there's a particularly strong type of intermolecular interaction called hydrogen bonding. Okay? If you have an OH or an NH in your molecule, that's a really polar bond. The H has a really partial positive charge, and the N or the O has a very partial negative charge. Okay? And so it turns out that silica gel has all these sort of ether-like oxygen, silicon, or silicon, oxygen, silicon bonds. But every once in a while, it also has a silicon, oxygen, OH. Okay? So silica gel itself can be involved in hydrogen bonding. Okay? The most important thing to take from this is that silica gel is sticky. Okay? And the more polar your molecule is, the more it sticks to it. Okay? If you have a non-polar molecule, then it doesn't stick to it near as much. Right? And that's going to be key. All right. So, you're going to make one of these plates. And you're going to draw a line and in the directions, and I printed out extra, by the way, if you guys don't have it. Some people print out their own versions, but I have some extra. Okay, you're going to do a line. I forget what I tell you to do it there, maybe a centimeter or something like that. Okay, and then on that line, you want to make just a little hash mark. Okay. I can't remember if I set it up exactly the same way in your instructions in there, but this will give you a general idea of how it works. Okay.
There's 5 lines.
Okay. Yeah. It doesn't matter. There's probably a code spot in there, perhaps.
Yeah.
Okay.
There was like a handout sent up yesterday. Or is it?
Yeah, code spot. Okay. All right. We'll add a code spot. Code spots are a little bit more complicated, but all right. Let's mess you up if the picture isn't exactly like your picture that you're going to do. All right. So, reaction. Starting material, reaction, product, and co. All right. Reaction. That's going to be stuff that you make. Okay. Students always want to write. They want to write product here. Well, that's. I always suggest students don't write product there. You don't know because when you say product, you mean aspirin. you don't have any verification yet that you've made aspirin. So keep it as reaction, or sometimes we'll call it reaction crude. Okay, it's your crude material. We haven't done any purification of it. We won't either. All right. Here is if you happen to have an actual sample of what you were trying to make, and we do. Okay, so we will put that on our plates. All right, and then I'll talk about co-spot in just a second. All right. Okay, and then SM is starting material. All right, because as I said, a lot of a common impurity that we get in organic reactions is unreacted starting material. Very common issue. All right, you are going to take your crude and dissolve it in a small amount of solvent, okay? And then you are going to take a capillary tube. There's two types of tubes here, and you need to be real sure which one, and they're actually different thickness, okay? So the capillary tube is thinner, and it's open at both sides. That's key. You're also going to use a melting point tube, okay? And the melting point is sealed at one side. Perfect. So, but for the TLC, you're going to use the capillary tube. You'll have your material dissolved in a small amount of solvent, okay? And you'll put the capillary tube in there, all right? And through capillary action, it will go up the tube a little bit, okay? And then when you touch this to silica gel, it actually sucks it back down. So it will make a little wet spot right on the TLC plate. All right? One critical thing about, and the verb we use is spotting the plate. One critical thing about spotting the plate is you don't want to just put the capillary tube and hold it down. Okay? We're going to run these up this plate. All right? Just similar to what you did in Gen Chem. And as they go up the plate, they tend to get bigger, all right? And if they get too big, then they start to obscure each other, they bleed into each other, as definitely you saw in the Gen Chem one, all right? So if you make the spot really big down here, then it's, you know, Jupiter when it gets up here. So you want the spot down here small, because you know it's going to grow, all right? And so how do you do that? You come here, and if you need more material on there, that's fine. Then you spot it multiple times. And I think I give you specific instructions in here on how many times you spot it. All right? So what you want to do is you want to pull it up fast, pull it up fast, pull it up fast. All right? You always do at least 2 of your reaction crudes. Okay? One where you've spotted it a couple of times, one where you've spotted it a couple of more times. All right? Because you don't know, you just took a small spatula tip. You don't know how concentrated your stuff is. All right, so you want to get sort of the big picture, not very concentrated, and you also want to see the nuance. That's when we spotted it more. All right. Okay. So I do my reaction crude, and then I will also come here, and we've got samples already made up in hood number 1, so you don't have to make up the samples. I forget how they labeled them back there, but remember in your mind what the names of these things are. Salicylic acid, okay, that's the starting material. The product is acetyl salicylic acid. Okay. All right. And so we go to the starting material, which is salicylic acid. I just had to spot that once. That's typically enough. And then the product we have over there, acetyl salicylic, we have product of aspirin. Okay. All right. And then okay. And then for the co-spot, what you're going to do is you're going to put 2 different things on there. Okay? You're going to put starting material. Okay. And then you're also going to come over here and get the other one, your reaction. And I'll explain what that's for in just a second. All right. You then are going to put it in a TLC chamber. Okay? TLC chamber has some type of solvent in there. All right. And We got tin foil, aluminum foil over the top. Okay. We put a piece of paper towel in here. All right. When you do that, is I do have the paper towel in the instructions, don't I? Okay. Go like that. That's all you need. And this makes the TLC go faster. I can tell students that. They always like that idea. Makes the experiment go faster. All right. If I've got the eluent in there, I put the paper towel in there, it will very quickly get the whole paper towel wet. And I can even kind of tilt it like that. And that will adhere itself to the side of the flask. Okay? That keeps the entire environment inside the TLC chamber sort of almost humid with that eluent. Okay? That keeps a lot of the eluent and keeps the TLC plate from drying out as it's going up the plate. All right. And you're then going to set your plate down in here. Okay. Usually it's at a steeper angle, actually. One critical thing that you need to be really sure of and look at when you're putting it in there is this line where you put all your stuff, that's got to be above the solution. Okay? If that line goes below the solution, it dissolves all your stuff off into down into the pond here, and the TLC doesn't work. Okay? You want the TLC plate to be down in the eluent and getting wet from the eluent, but you don't want that line to be underwater. For lack of a better way to say it. All right? Yeah.
So, do you have the top of it leaning on the side of the paper towel, or would you want it on another side?
You tend to, good question. Yeah, you tend to lean it on the paper towel, but you tend to, or you don't tend to, you always do. One side of this is smooth plastic, and the other is the silica gel. Try not to touch it with your fingers, by the way. You want to use gloves because the oils on your fingers can throw it off sometimes. And so you want the silica gel up. All right, so let's pretend there's eluent in there, okay? And then my TLC plate is going to go like that. Okay. So the TLC, the silica gel is facing away from the paper towel. Make sense? And then aluminum foil. Don't, by the way, create a complete cover of this thing because you need to watch this thing. So you want just enough so it goes over the lip. Okay, so a real small piece of aluminum foil. All right, and then through capillary action, in here, the eluent starts to crawl up the TLC plate. Okay, looking at it from this view, it starts to drag the things that you spotted on here up the TLC plate. Okay. All right. In general, we expect. Here's our, this is our starting material. This is our product. Okay. Remember I said that the more polar your molecule is, the more it sticks to silica gel. Okay? Which means it won't go as high because it's really sticking to it. Okay? If it's something very non-polar, doesn't stick to this, it's going to go right up the plate with the eluent. Okay? All right. Which one of these, top or bottom, do you think is more polar? They're both pretty polar, actually. I'm sorry, I heard it too. Bottom. Bottom is more polar? Close.
Top.
Yes! Have I used it? Okay,
Yeah.
I'll use it all year. I don't retire of it. All right, so why? You might think, oh, you know, here's another polar bond, and it's good thinking and stuff. Why the heck is this more polar? This is more polar because you